Yeah, I'm really a pure math person, and Martin told me about what this meeting was about, and that I should try to give a talk that appeals to everyone. I tried. I probably did not succeed, but at least this is one step in that direction. I decided a way. I thought that a way to maybe appeal to more people is to rather than going in depth on one particular problem, I try to talk about two different problems at the same time. So it's sort of two talks in one, and emphasize a particular aspect or two particular aspects maybe that could be interesting in other settings. And these two particular aspects are global analysis and microlocal tools. A motto of this talk could be think globally, act microlocal. So, okay. One of the projects, so the two things I talk about are black holes and stability of black holes on the one hand, and the other problem is boundary of rigidity. So, for example, well, somewhat simplified version of at this point, what it would be from a sort of mathematical theory perspective of imaging, say, the Earth. So, in some sense, what do black holes have to do with here the Earth? So, of course, not very much in terms of underlying physics, but something about the way we go about at least mathematically understanding that. And so the general relativity talk is part of the talk is joint work with Peter Hintz, who will talk on Friday about general relativity and inverse problems. And the inverse problems part is joined with Pam and Stefano and Gunther Woolman. So I hope that's something in common at the end of the day, actually quite early on. All right. So this is sort of both in linear and nonlinear settings. But in fact, the nonlinear aspects are not going to be very interesting. So I'm pretty much going to ignore them. Basically, what they mean, so this last paragraph here says, is that the linear analysis has to be done right. Like in a sufficiently robust and flexible and stable, that kind of thing, manner. And the reason why this is so is because in this black hole problem I will explain, it's a stability problem. So you're trying to understand a solution to the nonlinear equation near a known solution. It shows how little we know that even this was not known until very recently. It sounds simple, but not quite so. And in the case of the inverse problem, we're actually not really close to anything. It's not really a perturbation problem directly, but we make it so by making some choices. By sort of redefining the problem somewhat along the way, and then after this, we in fact can solve the original problem. So the main point is that the nonlinear nature of the problem is actually really not important. So I'm going to ignore them. So you might be. Various things can go quite wrong, and so it might require sophisticated nonlinear iterations like Nash-Moser or things like that, but I'm going to ignore this. And so the first point I want to make is that in all of these problems, you solve the linear problem globally on a certain underlying physical space. So you have a PDE on some domain, saying you're solving the problem globally on this. And this still leaves us some freedom in deciding what region of perhaps an even bigger physical space we care about this. But once you decide, you really have to work on it globally. So I will illustrate this in these cases. Let me just make some very general statements in the beginning, which is probably going to be boring, but it sort of sets things up. What happens once you decide this physical space, again, I will explain what sort of things go into this. So you have typically some sort of an underlying domain or manifold or something, so it's called M, and you have some operator on M. So more precisely, of course, so in the PDEs, you start to think about, once you start to think about an operator on its own, you really should be thinking about it as an operator acting between function spaces. So you really should come up with function spaces, and usually there's a lot of freedom, but of course, it's important that you actually can fix them. So not just vaguely talk about something, because usually that things will not work. And the other thing is that many choices are usually equivalent. Like in elliptic problems, nothing ever matters. You get the same thing, so why bother? But in other problems, choices do matter. A lot of choices are equivalent, but it's not to say that all choices are equivalent. So you have to be careful. For example, boundary conditions would be one example, but in global analysis of let's say hyperbolic PDEs, wave propagation, you can't really just think in the usual local way of what can happen, and you say nothing can happen. So in fact, things can happen. All right, so so this comes back to of course, so first Stokes, since after all, this is just an infinite dimensional version of AX equals B, right? You're trying to solve PU equals F at the linearized level, and so if you you may want to say that knowing F, what is U? So you want to solve an equation, that's a surjectivity statement. If you want to say that you can get U from F, that's an injectivity statement. All right, so because we are in infinite dimensions and we are trying to solve something about all functions or solve an equation, partial differential equation, so you really need to have estimates. I mean, you can't just say that in finite dimensions things go well. So it's usually easier, especially in the sense that there's a conceptual way of getting these. So, of course, part of the story will be getting these estimates. So that's where the microlocal tools will come in. But first, just abstractly, you need some sort of an estimate. And the estimate you need is that you need an almost injectivity estimate. So you can estimate Q in terms of PU. Well, you're going to commit an error. And so the key thing that you want about this error is that the inclusion map, so that's this U term on the right-hand side, the inclusion map from X to Z1 has to be a compact map. We want a similar estimate for the adjoint. So I will comment on this compactness in just a moment. So I think I have this on the next slide as well. Okay, so what does this compactness actually mean to get sort of feel for this? So where does this come from? This comes from typically, at the very least, that this target, the space on the right-hand side is sort of trivial, but if you want to think about this as a trivial space, is weaker in the sense of derivatives. So it has fewer derivatives. So you can control, say, the H3 norm of something, so 3 L2 derivatives, in terms of, say, just the L2 norm of that thing. I mean, plus, of course, the whatever norm of PU. Okay, but so that's something. But when you have a non-compact underlying space, so your domain is non-compact, then, or has a degenerate structure, that is to say that the operator on it, has a degenerate structure, then you usually need more, and the more you need is that the space on the right-hand side is also weaker in terms of decay. So rather than controlling, say, L2, that norm being in L2, it's in a weighted L2 space which allows growth. And so that's what will give you this so trivial for a pure analyst error. It's compact. You think of this trivial. All right. So of course, in real life, you'll often want invertibility on abstract grounds. It just tells you general nonsense grounds. It just tells you that you can get rid of the relatively compact term. So there's a finite dimensional obstacle. So if you have these estimates, first of all, the first estimate is the almost injectivity estimate. And to tell you that the kernel, so null space of P, is finite dimensional. The second one says that the range has finite codimension. Either one of them tells you that the range is closed. So so basically this tells you that infinite dimensions don't cause you trouble. Okay, so you often of course want an actual invertibility statement, and that amounts to, or left or right, so injectivity or surjectivity, and that amounts to saying that you can get rid of the last term of the estimate. But you can just show it, given this estimate, you can just really get at this, being able to get rid of the last term by showing that, in fact, any element of the null space, say, is trivial. And there are various techniques for doing that. So I will actually really concentrate on where these sort of estimates come from, because this is what what's robust. All right. So, so actually, this all sounds obvious, right? And in fact, when you try to solve elliptic partial differential equations, then I mean this is what everyone does. You really work globally. You cannot solve an elliptic PDE like Laplace's equation. You cannot, and you want to solve it in some big domain. You cannot solve it in a subdomain by just solving it locally, right? So that's not going to give you the solution you want. I mean, you have some boundary condition on the big domain. There's no translation. This is for the subdomain. But this is not. But so often you can. There's some other structure that lets you not do this. Just because you can, it doesn't mean it's a wise idea. So here's an example. So it's considered general relativity. So I'm not going to really go into the details because that's not important for what I talk about. So I'm going to talk about Kerr de Sitter black holes. So these are black holes in the universe with a positive cosmological constant, which, as of now, physicists believe ours is. So this is the real world. There are lots of black holes. Now, okay, so it's an explicit solution of Einstein's equation that you can just write down. Okay, so it solves the equation. Doesn't really matter what the equation is. It's a partial differential equation, not only a partial differential equation. For the metric tensor, which describes how space-time behaves. And so there are some parameters here, the mass and the angular momentum of the black hole. So a basic question is, okay, you could write down this explicit family of solutions, but the basic question is, suppose you perturb. So this is a tensor, so a matrix, if you want, on your space-time. And so the question is that suppose you perturb your initial data. And then, does the solution exist globally? I mean, does it blow up? Maybe it only exists for a finite time, and then something happens. So, okay, you have an explicit solution, but it doesn't mean that even a small perturbation will exist forever, as all the examples already will show you. All right. So, and if so, does it? I mean, so our picture is that over time. These sort of things should be tending to decay to a black hole, and then what we measure is gravitational radiation that's sort of coming out as seen as decay. And so that's what things like, well, actually, what gravitational wave detectors at this point can only detect only the initial signal, but maybe when they get more accurate and deal with noise better, they can see the actual decay, so the quasi-normal modes. Okay, so. So this is decay to the black hole. So this is just perturbing a single black hole. I mean, this is unfortunately not so easy. And then it's interesting. More than the universe than just one black hole, right? Okay, so the pair Hitri answered this affirmatively for slowly rotating black holes. So I've tried to say some things about the what goes into this analytic. So there are some subtleties. I'm saying this quite imprecise, and there are some subtleties because if one has a solution, so take the solution. You can express it in different coordinates. This is the diffeomorphism variance of the problem, and you get another solution. And there's a dual issue about how you specify initial data sort of constraints. There's some constraint equations that have to be satisfied. Okay, so there's some subtleties, but I'm going to mostly ignore these. The linearized version of this equation is a hyperbolic equation, so an evolution equation, so like a wave equation. Once you add gauge terms, so the gauge terms are to deal with this diffeomorphism variance issue, and so they don't really affect anything at the end of the day. But you have to be, I mean, once you do them right, they don't affect anything. But I'm going to ignore these. So once you get the wave equation, even a linear wave equation is perfectly good finite time solvability. So for any fixed finite amount of time, you can, if you have a solution, you can perturb it and get another solution. But of course, the perturbation typically expect that its size will go to zero. How much you can do if you want to solve for longer and longer times. Okay, so that's basically the usual ODE theory perspective, evolution equation perspective. So, but stability is really a global statement in space-time. So what we do is we use global analysis. So that is to say, rather than, so a typical way you want to think about nonlinear, or people think about nonlinear evolution equations, is that you solve them for finite time, and you somehow try to show, maybe by using some conserved quantities or quantities you can control, is that in fact you can keep iterating. So maybe you can go step size 1 uniformly, maybe under some a priori bound on your data. But here what happens is that we solve the linear problem globally, and we use that together with a nonlinear iteration. In this case, there are a lot of issues, so it's going to be a relatively complicated one, so an Moser iteration, to solve the nonlinear problem, rather than trying to use the step-by-step and uniform control approach. So for us, this physical space on which this operator lives is the total region of physical space in which stability holds. I mean, more precisely, in which you want to prove stability. So we need to develop tools for this non-elliptic global analysis. And then once you work globally, as I alluded to, there's more happening than just usual kind of picture one has for wave propagation that can just move around along what geodesics, not geodesics, or here to be, or not magnetism. So I hope to get to something about this towards the end. There are things like redshift and blue shift, so this means frequency going to 0 or up to infinity. There's trapping, so that's where the complications of the ODE, some sort of underlying Hamiltonian system, ODE system come in. And then there are sort of even more interesting, more global objects called resonances. These are these quasi-normal modes I mentioned, so sort of the ring down of a black hole. So these are really global objects, and global analysis gives you a straightforward way of dealing with these sort of things. And so this is actually where things like gauge modifications come in. Like, in which coordinates are you solving the equation? They don't actually pre-specify. We don't know. It's decided by this global nonlinear iteration on both the unknown metric tensor and the and this gauge parameter, which corresponds to these resonances in a fine-dimensional space. Okay, so it's good because of this to think about this problem globally. All right, so I just have a picture. So I'm not really going to explain precisely what happened, but you know the general attitude is that it's a PDE, right? So you're not supposed to take geometry too seriously when you start thinking about this. I mean, eventually it will matter, but it matters at the secondary level. Primary level, you want to have an underlying space, the physical space on which you have your equation, and you want to have your operator, and you want to say general things about analysis on this sort of space, and then it so happens that it has also some geometric extra information. So that's a secondary thing. Anyway, so the region that you're working with is going to be looking as follows. So I have a time interval, so I'm calling it T star. It's kind of a shifted version of the usual time, but so it's the usual thing in these general relativity problems. It's the sort of frame dragging. Starting at some initial time, T0. And then I have a radial variable, which in this case is going to be basically from R minus to R plus, but a bit in large. So this R minus and R plus are called the event and cosmological horizons. So this is a positive cosmological constant, so hence this cosmological horizon. So the R equals R minus is the event horizon that's usually here about for a black hole. And nothing is ever happening there, so that's not a scary place. The analysis just goes through it, so nothing matters. But we really, what we do is, so first of all, you have an initial surface. This is this T equals T0, also across the sphere. And again, the Curtis-Sitter metric is just some explicit metric on this domain. And so what you do is you have an initial hypersurface. This is this T star equals big T0. That's where you would impose initial conditions. And you have sort of final Cauchy hypersurfaces. So in a usual wave propagation, this would be like T star equals to big T0 plus 1. Okay? But these look a bit different here. They look vertical, so they sort of look like a time-like boundary. So like the boundary of a spatial domain. But in this analysis picture, that's on the left-hand side. Again, this is the analysis picture. You're not supposed to think that there's geometry yet. Okay, so that's what the domain looks like. But most importantly, we work up to infinite times. So at once. So all the linear analysis is taking place on this global operator, acting on global function space. So in particular, think it's mentioned in some other slide, but let me say it now. In these estimates, our compact errors have to actually have decay built into them. So that's an important aspect, and that's where resonances actually come in. All right. So now these Cauchy hypersurfaces are artificial boundaries in the sense that you choose them. Okay. So in this case, the choices don't really matter within reasonable limits. I mean, you know, there's like you never see the Cauchy hypersurface in real life. There's no such thing as time equals t0 or naturally given. Right? So and it's really not in the GR setting. I mean, locally, maybe you can make sense. It's not in the GR setting. So that's artificial. You cook it up, and it makes your life easy, but you cooked it up. So you got to choose it, but once you choose them, you really have to work globally on this domain. So the boundaries of the domain were a bit up to you, except infinity. Infinity is there because you want to do the stability problem. If you don't want to do stability, of course, you can stop earlier, but then you're not going to solve. Okay, so that's this is the global aspect. And what's on the right-hand side, by the way, I'm not really going to get into this, but this is the Penrose diagram, which basically the 45-degree lines would be the light rays. So in this picture, these upper boundaries, this r equals r minus epsilon, r plus epsilon, look more like a space-like boundary, like a future Cauchy hypersurface. And so that encodes the geometry, but it's a terrible representation of the analysis. So the left-hand side is analysis is geometry, except for maybe sometimes getting some intuition. All right. So let me just say a bit about where these estimates come from. So the simplest example, so in this setting, and I'm going to talk about the inverse problem, and then I'm going to talk more about these underlying tools. So the simplest example for Fredholm theory is, so getting these estimates, is elliptic operators on a compact manifold in that boundary, like a sphere or a torus. And nothing could be better than that. It's unbeatable. Right? In torus, if you just think about standard Laplacian, separate modes, all that, but the similar thing works not the similar thing in terms of the methods, but the similar conclusions work very variable coefficients and all that. So what happens, so let me just remind you what ellipticity is. So if a partial differential operator, then what you do is you replace all the derivatives. So first of all, so it's written like P, I think it's a local coordinate. So I have some coefficients and have some derivatives. And what I'm doing is I'm going to replace all the derivatives. So first of all, I want to take the highest order terms and replacing all the derivatives by the corresponding momentum, so dual variable. So like d psi j, so derivative in the psi j direction is replaced by psi j. And so ellipticity relates to the statement that this does not vanish when psi is non-zero. So for example, for a Laplacian, this would be just psi in the standard flat metric, it would be psi squared. For another metric, it would be some other quadratic positive definite form that varies with that. And so in this sort of setting, the spaces would be typically Sobolev spaces. So I'm calling HS, you might be calling WS2. So the target space, the domain space would be like HS. The target space would have m less derivatives. It's an m-folder operator. Then you're taking the dual spaces, and then the relatively compact spaces would have much fewer derivatives. You can take it wherever you want. And then the Fredholm property is really coming from elliptic estimates like this, either apply to P or P star. So if one is elliptic, so is the other. And what you do is you can estimate, elliptic estimates, you can estimate a function in terms of this elliptic operator by the function in M with m-less derivatives modulo relatively trivial. All right, so on the other hand, we have some non-elliptic problems, and what happens is that for these problems, we get estimates which look a little different. There's a loss of derivatives right here, so it's not s minus n, but s minus n plus 1. You need one more derivative than before, and so similar in the adjoint estimate. But this is still enough to imply that P is Fredholm, except that you have to slightly jazz up your domain, so you have to add an extra condition. So of course, it's trivial that this is a Hilbert space, but it's slightly less trivial. Like if I change this one in the wrong direction, it's not going to be necessarily true. Is that really trivial functions? So say simply the functions that that's in. But this is the limit how far you can go. So in any case, I want to dwell on this. I want to say that even though this is a non-elliptic problem, you will have Fredholm estimates for this. And as I already said, for this Lorentzian problem on a non-compact underlying space, so this time goes to infinity, I really need estimates in a weighted space. The errors have to be so that they are allowed to grow more in time. So the error norm is weaker in terms of growth. And that's how resonance is done. All right. So I'm going to switch to the inverse problems. And given how time is going, and probably much of the rest is going to be on inverse problems. So here the inverse problem is determining the distance function of a domain in the Riemannian manifold from the restriction. Determining the metric on the Riemannian manifold from a restriction of its distance function to the boundary of this domain. So in the case of something like Earth, so of course the anisotropic metrics aren't really Riemannian metrics, but if you had say an isotropic metric, or some anisotropic would be actually Riemannian. Anyway, what you are trying to say is if you know the travel times of waves, so that's a distance function, then you can figure out what's inside. So this is with Gunther and Martin, we are trying to go to the anisotropic world, but we'll see how that goes. Any case, there's an obstacle to doing this, namely diffeomorphism, so changes of coordinates. And so if you do a change of variables that preserves the boundary of the region, but rearranges somewhat the interior, in a mild manner, say, but still rearranges, you get a new metric that will still have the same boundary distance function. Now this obstacle doesn't show up in the nicest possible problem when you have a fixed conformal class, so this is what's really the Earth problem most like. You have a sound speed, be it P waves or S waves, and you have a background metric, which is the flat Euclidean metric, and you're trying to recover this, in that case, this conformal factor from this data. Okay, so it's pretty clear that you need some sort of geometric conditions. The standard formulation, Michel's conjecture, is to assume simplicity. So again, it's really not the specifics of this that I want to get into, but this is strictly convex boundary and the explanation happens to global diffeomorphism. And there's freedom there. This is a conjecture. You can come up with your own conjecture under other hypotheses. And so what we proved with Stefano and Ullmann is a rigidity statement. So this metric is determined up to the diffeomorphism invariance under a somewhat stronger hypothesis. So you increase the hypothesis, but in fact also on a different formulation which allows non-steeple manifolds. In fact, we in some sense generalize it, except that it's not really generalizations because we can't do everything that Michel conjectures. So there's a sort of slightly different, you could say in a different way that the conjecture should have been a bit different, at least given what we can prove. Michel's conjecture might quite well be true. All right. So okay. So again, the nonlinear aspects they do cause some trouble, but they're not sometimes not too serious. So it's related to gauge issues that they already suppressed for the Einstein's equation. So I'm going to suppress it again. So you might as well think about the linear problem, and the linear problem is about the geodesic X-ray transform. So what you do is you integrate a tensor along geodesics. You plug in the tangent vector of the geodesics in both slots of the tensor, so you get a function. The integral is then a function on the space of geodesics, or if you wish, as I'm going to reformulate it on your phase space. So position and direction in co-direction in which the direction geodesic is going. And then there's a simplified version where you just look at the scalar transform. So this. So here, f is just a scalar function, and you just integrate it on the geodesics and get again a function on the space of geodesics. Okay, so really you use a pseudo-linearization, but slightly different object, but they're going to behave the same way. So I'm going to ignore this. Okay, so in this case, it's really an injectivity problem that we are trying to deal with, or maybe injectivity with extra information like stability, blah blah blah. All right, so this I is is going from an underlying space, so say the domain, to a different space, namely the space of geodesics or points in phase space. And so that's an example of a non-square in various senses. And so it's much easier, it's usually inverse problems, to work with this normal operator, so I star I, or maybe sort of a preconditioned version, so I star QI, where Q is some sort of cutoff on the space of geodesics, say. Could be more complicated. And you might also, I mean, the star is expected to some sort of an inner product, but that's not really relevant. For this, you want to do the same phase space structure. All right, so anyway, under some geometric assumptions, so no conjugate points, this operator is an absolute differential operator, so more later, has much better solution theory than Fourier integral operators. In this particular problem, this goes back to Stefan and Luhmann. When you work globally on the domain, we'll try to change the problem in a moment. Okay, so one problem when you work globally, as from say Earth sciences, is that there can be conjugate points for the geodesics, which means that this is not really going to, it's not going to be absolute differential operator anymore. So there are going to be extra singularities for this operator. The other problem is that even if this doesn't happen, so say take something that's very nice, like the flat metric, and perturb it a bit. It's not going to happen. Nothing is going to go wrong geometrically. But what will go wrong is that you will still get this quote trivial unquote errors, namely compact errors, and you really want to get rid of them to solve the question. All right, and so what we do is sort of similar to how for the GR problem we could have these Cauchy hypersurfaces, except there they didn't really play any role. The real stuff was happening as T star went to infinity, is to localize this problem. So instead of solving it on this big domain omega, so omega tilde is this whole, I guess I put it before n actually. Anyway, this is big manifold in which you have this domain omega. Rather than solving it on all of omega, you're going to solve it on a smaller set O in it. And then you can actually proceed under some assumptions by sort of layer stripping argument. But I'm going to concentrate just on this O bit for what I want to say. Okay, so what you want to do here is just so think of this P is the point on the surface of the Earth, and you want to find out the sound speeds nearby, or really it's the linearized problem here, from knowing the integral of this of a function, which is basically the difference of sound speed, say 2 sound speed, integral of that along geodesics. So in sort of flat space with straight lines, hence the picture. And so the smallness of this region in which we work gives us a way to handle these compact terms, that error terms that showed up. So this smallness is what allows us to make them small, even though we're very far potentially from, say, the flat metric. Like when you are far in the interior, we're really far from it. At the surface, we are close to it, or whatever we know the metric at the surface. So whatever we know, we are close to that, if you just go a little bit in. And so that's what gives you the smallness of the arrow. And so small, of course, is really good. You can invert it in non-series. I mean, I propose that. So anyway, so you need, of course, some structure, underlying structure for the geodesics, because in general, why should there be geodesics that just stay in this set O? So right, so an important point is, so we decided we somehow fixed this O, and we want to find the function f on O from IF. The point is that we can only use geodesics that completely stay in this O, because if we try to use IF of gamma, where gamma crosses over here, we would really have to recover f here as well to really be of any use. So we have to only use geodesics that are local to this region. All right, so that sort of caps off, in some sense, our problem. So on the one hand, we have some freedom. We choose this O, so we choose an artificial boundary But on the other hand, we need to work globally on O. Can it just work on a subdomain? You're really going to have an operator, you really want to think of this operator on all of O, and say construct a left inverse for it. All right, so so this physical space is basically the domain O, where you can say that really in fact the initial boundary, so where this P lies, is completely irrelevant, because what you think is that you might as well just extend this unknown function f to be 0 outside, and so that just sort of constrains the support of f. So the original boundary is actually irrelevant. The real boundary is artificial boundary. Okay, so so good. And so we can achieve this if you make this O be a super level set of a function which has strictly concave level sets from super level set perspective. So let me just show the picture. It's probably easier. So here's my picture. So this is the original boundary. This is going to be a level. This other boundary of O is going to be a level set of this function x tilde. So I'm making x tilde growing like this, and I want this to be concave when you look at it from above. So I have all these level set, and at the end of the day, the smallest of O is going to say that, say the one through P is the 0 level set. Then I want a level set that goes close with C small. And so that's where we really solve the problem. So this new boundary I introduced, so I'm putting minus here, is that why I put this out? Yeah, okay. So this is the artificial boundary. It's not in the original problem. Just like Cauchy hypersurfaces don't exist in nature, this is artificial. But in terms of the analysis, it's more important than the original boundary, which is constraint support. Okay, there are lots of examples. All right, so maybe so about 5 minutes roughly. So I can't get really deep into this, but let me just say that the technical tool, so how you get these estimates is via microlocal analysis, so phase space analysis. And so the important thing is that that it is perturbation stable, so you don't need like rigid techniques that work when you have symmetries or things like that. And in fact, it also works in low regularity settings. So maybe the low is not one derivative. Maybe it's going to be 13, but 13 is a perfectly fine number for doing analysis. So low just means not arbitrarily high. You don't need things like C infinity. So I think a familiar, certainly what geoscience is perfectly familiar with. So really just working in doing analysis on phase space. So you have a position z and the dual variable momentum zeta, and what you're really trying to get at is, like, remember I said that these compact errors come from low regulative Sobolev spaces. So you're trying to get at singularities of say functions or distributions, and what they correspond to is high frequency behavior. So this zeta going out to infinity. So you really think of phase space as your underlying space. You're going M, we think it's just Euclidean space in Z, and really the sphere in zeta, where the sphere you shouldn't really think of as a metric sphere. I mean, you can, but that doesn't mean that you should. You should think of it as a very, very large sphere, which is really how you get out to. What does it mean that you go out to infinity? That means that you dilate this momentum variable by larger and larger constants. So what you really want is a transversal to these dilation orbits that are really going on. All right. And then, for example, they already alluded to, this is anyway what's happening in this inverse problem. You're supposed to think about geodesics. What are geodesics? Well, you think of them in phase space. Then you have an energy function. You have from this you get the Hamilton vector field. It's the Hamiltonian point of view of classical mechanics. And then, for example, the space of geodesics, you can just think of it being somewhat over-parametrized by the say even the unit sphere bundle of Rn, because you have to identify them different points on the equivalent. Okay, and then maybe the only thing I can say about this, and so pseudo-differential operators then come from quantizing nice, in some sense, functions on phase space. So nice means that in some sense, I mean, it's not quite this, but it's good. I think it's gives a good feel for it. Asymptotically homogeneous with respect to dilation. So they behave like a power of zeta as zeta goes to infinity. So for example, in this inverse problem, this I star I would be roughly the inverse of the length function with respect to the metric. And another thing you can think about is what is local. So now you can localize in phase space. So localize simultaneously momentum and position. So this works modulo lower order, like in terms of differential, pseudo-differential operators, modulo lower order operators. That's the reflection of the Austrian principle here. So it's in quantum mechanics. In some sense, you're doing it without there's no quantum particles floating around. Okay. So for example, what does it mean that you localize to a point in phase space? So really remember, this is the orbit. You're really going out to infinity in momentum. What this means is that you take an operator, which you can think of as homogeneous of degree 0, so invariant under dilation. So it's a function of x and I call it z and zeta over both zeta. Just think about just a cutoff function of the sphere. So that's what we localize. Okay, and then so maybe I'm going to skip over this. And so, for example, these sort of things give you even a Microlocal, so local in phase space version of elliptic estimates. Okay, various things, and there's and then once you get to non-elliptic problems like wave equations, then you have a propagation phenomenon in phase space, and so that basically looks like this. So this is now a phase space picture here, the Hamilton vector field orbits, and roughly speaking, the sort of things you have is that if you control a function in some space of phase space, you control it later on using the Hamilton flow. And then when you want to go to this actual GR problem, then the more exciting things happen somehow at infinity, which you can think, one nice way of thinking about this is you compactify phase space, and once you do so at infinity, or space at infinity, I should say, once you do so, your Hamilton flow will have critical points, and we have to understand how you propagate stuff through for example, saddle points of the flow. That's, by the way, this reaction evolution. That's all it is, propagation through saddle points. There's a picture. All right. So, okay. So let me just very quickly say what happens in this inverse problem. So what happens here is what we're going to do, because you can only use geodesics that stay in this region. So they're roughly tangential to the original boundary, and even more precisely, they're going to be, when you go all the way to the artificial boundary, they have to be tangent to it, otherwise they would cross it. So you have to localize roughly tangential rays, so you consider something like this, and then this Q is going to be a cutoff in the direction. This angle of the cutoff has to go to 0 as you approach the boundary of this region. Now, if I didn't have to scale things down, I could just choose a cutoff, wherever, then you can compute the principal symbol of this operator. So what is the leading order? It's the differential operator. You see that it's elliptic under assumption that given any codirection, zeta, there's another codirection c, such that the corresponding geodesic, so you have a positive weight. So in other words, this Q is positive, so you take it into account in this transform. So when you're however, we have to scale down this angle to 0, and so you have to decide, because you have to be tangential as you approach this artificial boundary. So again, that's the only real object here, the artificial boundary. And so the sort of freedom you have is how you scale it down. Like how big of an angle do you take? It has to be certainly small enough that the geodesics don't cross, but that allows roughly square root of the distance from the artificial boundary. We actually take a smaller one, because this choice gives you a different pseudo-differential operator algebra at the end of the day. And so with the smaller choice, we actually reduce to the most standard pseudo-differential operator on Rn in some sense, but this artificial boundary, but in this picture, gets pushed out to infinity. So I don't think I have time on it, time for this, but let me just say these 2 paragraphs, is that, so here x equals 0, that's the artificial boundary. Now, if I just think locally for now, it's not a good idea as I said, but for now I just think locally. So you have coordinate x is the normal variable, x equals 0 is the boundary, so x is positive in the interior, y is some coordinates along the boundary or level sets. And so one choice you could take is, for example, of pseudo-differential operators which are generated by vector fields like this. So these are exactly the vector fields tangent to the boundary. So dd by j is just tangent, obviously. It's not doing anything in x. X ddx is at tangent because it vanishes at x equals 0. Okay, and so for example, the GR problem is in fact exactly this if you compactify your spacetime by making x e to the minus t star. This is the exponential, and this is actually the exponential decay of the metric to curves. And then, but for our problem, the sort of values you get are based on x squared dx and x dy. This is a completely different pseudo differential operator algebra. It has much better properties, and in that, so everything is somewhat purely symbolic. So the same way as you could understand elliptic problems by constructing an approximate inverse, just parametrics by just inverting the principal symbol. We can do it the same way